Hey everybody, and welcome back to Calc 3 Online. So directional derivatives are so important, so I want to take 2 days to talk about them. And the plan for today's video is really just to do some kind of other examples using directional derivatives. So a lot of times we get things like this question in the real world with applied math. So the idea is find directions in which a directional derivative of some surface or something at a point has a certain value, which honestly becomes probably a much more important problem. I don't know, it's probably equally as important as finding a value in a certain direction too, but you should know how to do it. So we're going to need the gradient. So we're going to take gradient of f, which is just all of our partial derivatives like f with respect to x, which would be negative y squared e to the negative xy. And then f with respect to y, you have to do chain rule. You're going to get, product rule. You're going to get e to the negative xy minus xy e to the negative xy. And we need the grad at 0, 2. And if you go and plug everything in, you should get negative 4, 1. All right, so what we really want is this vector. We want to dot it with some vector and have it be 1. But it needs this xy vector that we're going to solve for is like a unit vector. So from this, right, we could get that negative 4x plus y equals 1. And this is probably the trickiest little step. So since it's a unit vector, we would need it to satisfy something else of length 1 in any direction, which kind of should make you think like circle, unit circle. So, the idea is whatever vector we have, right? It doesn't matter which direction you're in. These are horrible arrows, but basically they all have to satisfy this equation. So now we just have a system of 2 nonlinear equations, and I'm probably just going to do substitution. So from here, I'm going to take that, and I'm going to do y equals 1 plus 4x, and then I'm going to sub in down here, right? So x squared plus 1 plus 4x, all of that squared equals 1. And I think you guys can solve this. I'm just going to write down, you should get from that 0 or negative 8/17. And then that means if you plug into this up here, y equals 1 plus 4 times 0, which equals 1, or y equals 1 plus 4 times negative 8/17, which equals negative 15/17. So you basically get these 2 directions. You get either 0, 1, right? Or you get negative 8/17 and negative 15/17. So those 2 directions, if you do the directional derivative of this at that point in these 2 directions, they both would give you value 1. All right, so this question says that suppose the temperature at a point in space is given by this t of xyz function, and t is measured in Celsius, and xyz is in meters. And the question is kind of 2 parts. So in which direction does the temp increase fastest at the point 1, 1, negative 2? And what is the maximum rate of increase? So we talked about this last time in the last video. We were saying that, since this directional derivative is really this scalar projection, if you basically don't move its direction and you just go in the direction of the gradient, that would always be the fastest increase or decrease. The negative of it would be the fastest decrease, right? So what we really just need to do here is find the gradient of t and then evaluate the gradient at the point, and we'll have the first part of the question there. And then the maximum rate of increase is literally just finding the magnitude of the gradient. So that's the plan. First we're going to find the gradient of t. And it's kind of a messy function, but it's also not that bad because I guess I'll write this here. If you think of it this way, 1 plus x squared plus 2y squared plus 3z squared. If you think all of that to the -1, then you don't really have to think like quotient rule or something. You can just think product rule, and so you really just do like a chain rule now. So you'll drop that -1 to a -2 with the derivative, and then you'll multiply by the derivative of the inside for whatever x, y, or z you're kind of working with. So if you do that, you'll get like -160x over 1 plus x squared plus 2y squared plus 3z squared, all of that squared now, because that's doing like 2x times 80 on the top, and the negative comes from, bringing this power down, basically. So I think I'm just gonna, basically that just in every term. I think I'm just gonna write out the other ones now quick. All right, so that big messy thing is the gradient. And then we need the gradient of t at 1, 1, -2. And this is just a lot of plugging in. It's not horrible because you get a lot of ones, which is kind of nice. But if you go and do this, you should see that you get 5/8 times the vector -1, -2, 6. Okay? And so that is basically like part A, in a sense, like this part, the direction in which the temp increases fastest. And then the maximum rate of increase, this part down here, you basically just need the magnitude of the gradient at that point. Okay? And if you do that, you get 5/8 square root of 41, which is like approximately 4 degrees Celsius. So this is just kind of a good application kind of problem to see how we can use that really important idea of like the max increase or decrease kind of thing. So that notion of the gradient descent and following the gradient to get to a local max or min is a very common trick that we use a lot, and that's kind of related to what we're doing here.